Hello everyone. Today we're going to discuss how to use seismic data to constrain permeability models of reactivated natural fractures from hydraulic fracture stimulation. Or a shorter version of the topic would be quick evaluation for optimal recovery in unconventional reservoirs. As we know in our business, everything starts with the economics. And some of the typical questions that we ask when we start the development is what is the expected recovery? What is the initial production? Or what is the optimal spacing between hydraulic stimulation stages? What is the optimal well spacing? And this is just a sample of the long list of questions that we have. And to answer these questions, we need a multidisciplinary approach. And for instance, we need to know the stress state and the stress variability, and that belongs to the area of geomechanics. We need to know hydraulic fractures geometry, permeabilities, and fluid pressures, and that has to do a lot with completion engineering. We need to know matrix properties that comes from geology and geophysics that we are not going to be discussing in these presentations, although that is very, very extremely important. And we need to know the properties of the natural fractures that also comes from the fields of geology and geophysics. But the essence of what we'll be discussing in this presentation is that existing natural fractures play a fundamental role in the success of drainage after hydraulic stimulation. Natural fractures are important if they flow. So let's start by reviewing some basic geomechanics concepts related to the natural fractures quality in unconventional reservoirs. But before we talk about unconventional reservoirs, let's see what happens in conventional reservoirs. In this case, some natural fractures might be conductive for a given pore pressure. And here's a figure from the book of Mark Sobak of 2007, where he shows conceptually what is going on. So here are some fractures, red and blue fractures with different orientations with respect to the maximum horizontal stress. And when you plot these fractures in these plots of shear stress versus effective normal stress, what you see is that some of the fractures, they will plot above the friction line, and some of them will fall below the friction line. The fractures that fall above the friction line are the ones that are called mechanically active, and they tend to be conductive, whereas and they are also called the critical stress fractures. Whereas the fractures that are that fall below the friction line are the ones that are mechanically dead or close. So we're interested in these fractures, which are the fractures that flow. And as we see, there is a dependence on the effective normal stress on the pore pressure that will be crucial to understand what is going on in unconventionals. Unlike conventional reservoirs where some fractures may be originally open, in unconventional reservoirs, most fractures are closed in original reservoir conditions. So here's what happens. This figure is an interpretation of an Eagleford outcrop that I modified from a paper from Ferrell and others. And what I did was that I copied their interpretation until I filled an area of a typical seismic beam. And the result is that you can get a few thousand joints and a few faults inside that beam. Then, when we create a hydraulic fracture with high fluid pressure, fluid will leak off through these fractures or through these joints, reactivating some of them that were originally closed. And as reactivation occurs, some of them will make some noise that can be detected as a microseismic event. And our assumption is that that process of reactivation can be described using the Moore-Cullen faulting theory. And so in this presentation, I will describe our approach to obtain the effective permeability of systems like this. As we increase the fluid pressure, more fractures will get reactivated, but that will occur up to a limit. So here are our conceptual fractures, and here is how these fractures plot in the effective normal stress versus shear stress domain. As we can see, at original reservoir pressures, all these fractures fall below the friction line. when we increase the fluid pressure, the fractures that is closer to the friction line will get reactivated first. And the pressure needed for reactivation is given by this expression that depends on the effective normal stress, the shear stress, and the friction coefficient. Then, as we keep increasing the fluid pressure, other fractures that are poorly oriented will also get reactivated until we reach the hydrofracture limit that we are going to assume is close to the minimum horizontal stress. And what we see is that fractures that are not reactivated when we reach this limit will remain close. Like these green fractures, they will be impossible to reactivate. As we explained in the previous slide, fluid pressure is a critical parameter. But not only the fluid pressure at the well, but also the pressure decay away from the well. Here we have two conceptual figures from Mukuhira and others that show the schematic pore pressure behavior over the entire reservoir before shut-in and after shut-in. And yes, these decay functions are very difficult to estimate, but we can use in some cases, for instance, microseismic data to at least approximate their extent or where these functions will decay to zero pressure. Here's an example of the application of these concepts from a paper by Sobak and Lonsny. What they do is that using orientation of natural fractures from FMI data along horizontal wells and the geomechanical parameters that describe the stress field, they show how fracture orientations, natural fracture orientations get reactivated as fluid pressure increases. So in this figure, they start by reactivating a single fracture, and as the fluid pressure is increased, more and more fractures are reactivated until they reach the hydrofracture limit. So at the end, they have two types of fractures. They're red fractures that are the reactivated fractures that effectively create the network, and the black fractures that remain closed. They are impossible to reactivate, and they are mostly perpendicular or quasi-perpendicular to the maximum horizontal stress. So this work for us is important because it serves as the inspiration for the work you are going to see in the rest of the presentation. We ask ourselves, can we generalize this concept to 3D by estimating natural fracture orientations from 3D data? So this is what I'm going to explain in the rest of the presentation. The question is then, how do we use seismic data to estimate fracture orientations? So in the next few slides, I will show a brief summary of how we do that with an example from the Eagleford formation. We start by generating structural attributes from the original seismic amplitude data. In this example, we use maximum curvature, but to answer the question of which attribute to use, the selection of that attribute will depend on which one gives better results when compared with independent data. So quality control is a key. In this figure, we see faulting along different orientations in an area of approximately 10 billion square feet, which is roughly the size of a large city. Then we compute local strikes from the structural attribute by estimating the local gradients of the data. This figure shows local strike orientations using a circular color scale. These green colors represent orientations north 45 east, which seems to be the dominant orientations, whereas the yellow colors represent the secondary north 45 west orientations. So the question is, are these actual natural fractures orientations? Well, the answer is not yet, until we compare them with actual natural fractures orientation from independent data. So here's the first comparison. We used the orientation from outcrop data that I showed earlier to identify sets of fractures at a much smaller scale, which is approximately 10,000 square feet. We see at this scale the same two families that we observed in the previous scale, a larger city scale, which is one family of long joints at approximately north 45 east, and a second family of shorter joints at approximately north 45 west. In this area, we also had access to moment tensor inversion results from microseismic data recorded with the surface array. These blue lines represent the trajectories of the horizontal wells in the area of interest, which is roughly 1 million square feet. From these inversion results, we observe again the same two families of orientations. We see a green family, which is north 45 east approximately, and then we also see a second yellow family north 45 west. In this case, these are the orientations of reactivated natural fractures from the hydraulic stimulation. Here is the histogram of these orientations, again being the north 45 east family more abundant than the north 45 west yellow family. Finally, when we extract the orientations derived from seismic data just in a volume around a well path, which will be the well of interest for the rest of the presentation, this is what we get. Here is the well path of interest. Here is the volume of maximum curvature around that well path. Here are the orientations derived from the curvature, and here is the histogram of these orientations. Again, we observe the same two families of orientations, north 45 east, north 45 west, or the yellow family. What we have seen with this example is that orientations from actual natural fracture data at different scales and orientations derived from seismic data also at different scales are consistent with each other, which give us confidence in using orientation from seismic data as a proxy for the orientations of actual natural fractures around this well path. As I said, now that we have a proxy for natural fractures orientations in 3D, we will focus the remaining of this presentation in examining the problem of fracture reactivation around this well. Now that we have fractures orientations in 3D, let's go back to the geomechanics and the estimation of flow parameters. The first step is to start with the geomechanics point measurements. The geomechanics information we had in this case was in the form of point geomechanic measurements for a given depth. We knew this is a normal faulting regime because we had vertical stress, because we had maximum horizontal stress, we had minimum stress, we had also pore pressure, and we can see here some overpressure in the system. We have the friction coefficient, and we have also the orientation of the maximum horizontal stress. When we plot the stress state that corresponds to this parameter in the effective normal stress versus shear stress domain, what we get are more circles that are below the friction line, which indicates that the natural fractures are closed. So in the next slides, we will see what happens when we increase the fluid pressure and move the more circles to the left, and we'll have then some points above the friction line. So this is what we will examine next. The second step is to use geomechanics gradients from the previous slide to populate a 3D volume around the well path. So from the calculated point gradients in the previous slide, we generate volumes of vertical stress, maximum horizontal stress, minimum horizontal stress, and pore pressure. And here is where I have to emphasize that if we have additional information about the stresses and pore pressure, let's say from more well data or from seismic data, we can introduce that at this point to have more variability in these volumes. But in this case, again, the only information we had came in the form of point measurements at a single depth. The third step is to introduce hydraulic fracture geometries and fluid pressure functions away from the hydraulic fractures. So here's what we do. With respect to the hydraulic fractures, we assume a geometry and orientation that in this case will be parallel to SH max. Then we assume a pressure behavior inside and outside the hydraulic fractures. Inside, we're going to assume that the pressure is constant, and outside, we're going to assume a linear decay away from the hydraulic fractures. What is the extent of this decay? Well, we don't know exactly, but in this case, we're going to use microseismic data to help us guess the maximum distance at which this function goes to zero, and we will use this as an initial guess. Of course, if we have other information, we can model the hydraulic fractures and pressures using different assumptions. Once we have volumes of fracture orientations, stress state, and fluid pressures related to the hydraulic fracture geometry that we have assumed, we arrive to the fourth step, which is to estimate the distance, actually the fluid pressure, between each fracture and the friction line using the pressure equation that I showed at the beginning of the presentation. As we said before, when we increase the fluid pressure, we effectively move to the left the fracture cloud in the effective normal stress versus shear stress domain. These fractures that are above the friction lines are the fractures that become conductive, and the others are closed. When we plot the location of the different fractures, either reactivated or closed, in actual 3D space, what we see is a heterogeneous distribution that corresponds to the variability of natural fractures orientations that comes from seismic data. Finally, once we have a volume of reactivated and closed fractures, we arrive at the estimation of effective permeability. And for that, we are going to use the odd upscaling equation. This column here at the left shows the effective permeability of reactivated fractures inside the hydraulic fractures and in the estimated reservoir volume outside the hydraulic fractures. As you can see, they are very heterogeneous. And to understand these heterogeneities, all we need to do is examine the fracture orientations estimated from the seismic data, which are here at the right. So for this particular fracture, for instance, we see small permeabilities that correspond to fracture orientations that are quasi-perpendicular to the orientation of the maximum horizontal stress. Remember, this is the yellow family. And the same can be said about the heterogeneities of the permeabilities in the stimulated reservoir volume outside the hydraulic fracture. Here is the orientation of maximum permeability that results from the upscaling that is also very heterogeneous. So after this analysis, we get permeabilities, we get orientations of permeabilities, and we get other flow parameters. But the question is now, what do we do with these flow parameters besides understanding their heterogeneities and identifying areas more prone to reactivation? We use these parameters to model productivity of different design scenarios using flow simulation and select the optimal design based on economic considerations. So here are some scenarios that we model, like well path orientation, location, number, and shape of hydraulic fractures, pressure function decays, frac barriers, fracture apertures, the seismic attributes that we use to generate the fracture orientations, depleted areas, and so on. So here's an example. We generate different scenarios of geometries of hydraulic stages and fluid pressures. The different cases consist of 11 long hydraulic stages, 16 long hydraulic stages, and 21 short hydraulic stages. For the long and short stages, we assume different pressure decay functions inside and outside the hydraulic fractures. Once we generate these scenarios of hydraulic fractures and pressures, we pass them through the workflow I explained before, and we end up with volumes of flow parameters for each of them. Then we import these volumes into a flow simulator. And the goal is to assess the production uncertainties related to the different scenarios. In our particular example, we obtained that the Q production for each scenario after 5 years is very similar for the 3 cases. And we see the benefit of adding more stages only in the long term. Here is the 21 stages case. Of course, this is just to illustrate the workflow and cannot be generalized to all cases. The idea is that at the end of the day, once we've modeled different scenarios that incorporate all our assumptions, we select the best one based on economic considerations. As I said at the beginning, we didn't consider metrics properties in this presentation, but we can include 3D rock properties, mechanical facies, and pore pressures from well and seismic data for better spatial modeling of the stress variability. Also, we can include conceptual results from hydraulic fracture modeling software for better representation of the hydraulic fractures. And finally, we can use this workflow as a screening tool to prioritize large development areas depending on basic geomechanics and geologic considerations. So in summary, 3D seismic data can be used to constrain flow parameters of reactivated natural fractures. We start by computing the seismic structural attribute, then we compute and QC fracture orientations, and by bringing additional concepts and data related to stresses, pore pressure, microseismic data, hydraulic fractures, and also metrics properties, we can decide which fractures are going to be conductive. Then after upscaling and calibration with production data, we can estimate permeabilities and flow directions for different scenarios. And these flow parameters are used then to estimate the expected variability in production behavior. Well, that's all I have to say. Thank you very much for your attention.